Hello, everyone. It's my pleasure to be here to talk to you about Galaxy Zoo and use of Galaxy Zoo in the classroom. My name is Karen Masters. I'm a professor at Haverford College, which is near Philadelphia in the United States, and I'm the principal investigator for the Galaxy Zoo at present. So I've been asked to give a talk both about Galaxy Zoo in general, what we're doing with it, and how we use it to understand galaxies in the universe, and also a slightly interactive workshop about how you might be able to use Galaxy Zoo in your own classrooms. Okay, so what is Galaxy Zoo? Well, the short answer is that it is a solution to the big data problem in astronomy. And so back in the early 2000s, the Sloan Digital Sky Survey put out its initial sample of 1 million galaxies, so 1 million images of galaxies and redshift, so physical properties could be measured. So how do you deal with this as an astronomer? Well, one way was to turn galaxies into data points. And in fact, obviously, we still continue to do this today. And there's a variety of these plots which show, this is a histogram of the colors of galaxies showing they're primarily in two colors, blue and red. This is the color magnitude diagram showing that more massive galaxies or brighter galaxies tend to be redder. Or measurements about the mass in stars and galaxy compared to how metal enriched they are. This very famous plot in extragalactic astronomy showing that more massive galaxies tend to have more metal enriched gas in them. But we lose something. There's information in the morphology of galaxies, and morphology was much harder to turn into a single number. And so in the middle here, I have a 15 by 15 set of images of the galaxies from the Sloan Digital Survey sample, showing just the wide variety and diversity of structures and shapes you can see in galaxies. So certainly back in 2000 and even today, I hope to convince you this is a hard problem to do with computers, but really quite straightforward for people. We could tell people that this is a spiral galaxy and this is an elliptical galaxy, and then just ask them to go ahead and classify images of galaxies we couldn't look at for ourselves. The current website for Galaxy Zoo looks a little bit different to that. This is actually JWST images of galaxies at two different kind of color balances and stretches just to show different features, but we're still asking pretty simple questions. So is the galaxy smooth, or does it have features of a disk, or is it an artifact? For every set of questions, there's going to be a help button, so you can ask for help with the task. There's also a field guide and a tutorial. We don't just ask these days spiral or elliptical, we'll ask a series of simple questions about what you see in a galaxy so we can reveal all different kinds of structures. This one I would call features or a disk, but it's a pretty edge on disk, isn't it? We've been doing this now, I think, for 18 years, not 17 years, and on a whole variety of different imaging data sets for galaxies. So we have classified the entirety of the Sloan main galaxy sample, that 1 million galaxies, plus the brightest quarter of it with more detail. We have classified all of the public imaging from the Hubble Space Telescope. Euclid's was an infrared survey. Illustris is simulated galaxies, which we classified in the Galaxy Zoo method to see how well the simulated galaxies match the population in the real universe. DESI and DECALS has been classified, which is a kind of very Sloan-like, but with a bigger telescope survey that is ongoing at present. Subaru telescope. What's currently going on is that we have James Webb telescope images on the site, JWST. We've done classifications for one set, the Sears set, which is one of the extragalactic surveys that was approved. And Cosmos Webb is the biggest one, and that's what's currently on the site. We also very recently finished classifying a set from the Euclid Space Telescope, which is an ESA mission. This was all pretty nice collaboration with Euclid Science Collaboration, where Galaxy Zoo, with our machine learning buddy Zoobot, was in the loop of the kind of initial data processing for for Euclid. What's coming next, we hope, are Vera Rubin telescope images. So we've been working on getting the color balance and the cutouts right for that. And we were really excited to recently learn we got funding from NASA, which hopefully should still come through to get a postdoc to work here at Haverford and be able to work hopefully more quickly on that color balance and cutout issue so that we can hopefully get Roman Space Telescope images of galaxies on the Galaxy Zoo site as quickly as possible, as quickly as they're available. All of this has been super successful and kind of opened up this box of crowdsourcing as a real nice way of doing data analysis. So back in 2010, my colleague Chris Lintott, who was the original PI of Galaxy Zoo and the founding PI, I'm still involved, but decided to step back from leadership. So it was my honor to take over from Chris. But Chris realized that this technique could be used not just for galaxies, but for all kinds of data analysis. And so the Zooniverse was launched, inspired by the Galaxy Zoo and now much bigger than the Galaxy Zoo and our sort of parent organization. There are millions of users at Zooniverse and many, many different projects using this crowdsourcing technique across all different kinds of areas of research. And you can make your own project, which is pretty fun and something you can think about how you might use in teaching, actually, in addition to being a really useful research tool. You can launch your own project privately without any interaction with the Zooniverse folks. If you want it to be publicized and become a formal Zooniverse project, there's a peer review process that you have to go through. Okay, so back to Galaxy Zoo, what do we do with our classifications? Well, I just want to really reiterate that we collect multiple answers per question. So we're going to have 20 to 40 people answering each question. And so again, it's kind of like a tree of questions, but if you just think about the top level, 20 to 40 people answering whether they think they see a spiral or an elliptical. We would call this the answer, the balance of those answers, the raw vote fraction. We then do some algorithms which will weight users by consistency. We don't have huge problems with this, but if there's anyone going through classifying randomly, we want to kind of clean that out. So we do have some quick checks for consistency, and we'll clean out any answers from anyone who consistently disagrees. In many phases, we correct at this point for observational biases. Galaxies look smoother if they're further away, just because you can see less. That is, the users are answering what they see in the images, but we want to get at the physics. So this is not about correcting the users' classifications at all. This is just about correcting for the physics, basically, that further away objects look smoother. And you can read about how we do that in a series of papers where it's been implemented. And this gives us our de-biased classification likelihoods. These are numbers that vary from 0 to 1 typically, that see how likely we think it is that a certain feature is present in a galaxy. So sometimes we call these p-spiral, p-bar. They're a little bit like probabilities, but they're not formally probabilities. But they are numbers that vary from 0 to 1 that tell you about what features are visible. For a single galaxy, that kind of looks like this. So this is a visualization of classifications of this of NGC 2771, which is a classic barred spiral galaxy with an intermediate bulge. In Galaxy Zoo, we can see that 39.019 people classified this. That's revealing that weighting for consistency, down weighting approximately an entire person. 38 of those 39-ish people said they saw features or a disk. So we're really confident that this is a galaxy with features. There's always one, but with 38 out of 39, that's a really high vote fraction. And so we know it has features. Of these 38, 37 say it's a face-on disk, which I would agree with. 35 say they see a bar, and you see so on and so forth down at these more, like further down the classification tree questions, things get a bit more ambiguous, but we still have useful information. And if things are about 50-50 for a specific galaxy, that's also useful information. That tells us that galaxy was hard to classify. So this is all incredibly useful, and we've used it in many, many peer-reviewed papers at this point. For a long time, we've been worried about the future of Galaxy Zoo and how this might scale to future surveys. I've been using a version of this slide apparently for more than a decade. And in fact, this is talking about the future being Euclid. And of course, Euclid is now happening. But the idea was in Euclid, you end up with not 1 million galaxies like in the Sloan sample, but you might get 2 billion galaxies with that kind of physical resolution, with that kind of imaging quality. And back in 2012, we said this is 70 years of Galaxy Zoo effort and clearly not possible, and was used by a number of people to motivate that machine learning was going to take over. We can actually do better now, though. And so let me talk about that. I'm often going to be asked when I talk about Galaxy Zoo, why aren't we just feeding this to the machine? We just give the galaxy images to a machine learning algorithm and we can do science from that. Well, machine learning has some complications. It kind of broadly falls into two categories, right? Supervised machines where you have a training set, you teach the machine basically to identify stuff in your training set, and then it applies that to unknown data. But the thing is, you need a training set that's pretty large to be able to do that, particularly if you have rare objects, and we do enjoy rare objects in galaxies. And so we need a large enough training set to be able to train our machine. Where are you getting that from? Well, Galaxy Zoo, typically. There is unsupervised machine learning. So this is sort of clustering similar looking objects. That's very interesting, particularly for finding weird objects that are unusual. But you still need some human interaction to kind of figure out what the clusters are physically and what to do at the other end. And so we'd argue that's just moving the crowdsourcing or the human interaction to the other side of the machine. And there's these days an enormous number of papers with some nice reviews of how machine learning is already being used in galaxy evolution and astronomy in general. Galaxies are complicated for machines. They're patchy, they have foreground stars, they have image artifacts, they have all kinds of things going on that humans are quite good at filtering out, but machines kind of can end up focusing on these. This turns them into a hard machine learning problem, much like the identify whether or not it's a puppy or a bagel, used to great effect in Mitchell's versus the Machines to defeat the robot or the attempted robot invaders with a pug, which they can't tell if it's a dog, a pig, or a loaf of bread. And even some of those security checks online are using the fact that galaxies are complicated to identify humans. None of those are real spirals, which is fun for me. That doesn't mean machine learning's not useful. And in particular, in Galaxy Zoo, we've had a number of papers about our ZooBot machine learner. This is a supervised Bayesian CNN for those who want the terminology. We train it with a training set that's coming from the crowd. So we train it with the images we want to apply it to with a subset of it. ZooBot then can learn really nicely to help classify the simple objects and kind of cleans out the boring things to classify, but it will feed back things that it's not sure about. That's kind of what the Bayesian part of this is. It comes out with a sort of certainty probability as well as what it thinks the galaxy is. So for the uncertain things that ZooBot classifies, we can feed them back to the crowd and improve the training set. And all of this helps us do science. And there's a series of papers by Mike Walmsley, who's a fantastic PhD student now, then postdoc, working in the team on machine learning. So are we done? Have we trained ZooBot and it can just move on with classifying all the galaxies? Well, we think no. And we think no, partly because galaxies look so different in different surveys. So there's an example here of a galaxy in SDSS, the same galaxy in Deckel's imaging, HST and JWST. And you can see that the morphology, the structures that you see just looks different at different wavelengths and at different physical resolutions, different surface brightness. Mike Walmsley, again, has a nice paper where they kind of prove that you do a lot better with machine learning if you retrain it on the actual images that you want to classify. And so we think there's always going to be a place for the crowd to help with training sets for machines. So yeah, we're keeping doing this. But these days, we pretty much always have ZooBot in the loop as well. So we're kind of the nice collaboration between humans and the machine. Moving on to other reasons why we'd like to keep doing Galaxy Zoo, people ask questions you don't ask. So the most famous example of that in Galaxy Zoo is something called Hanny's voorwerp. Hanny van Arkel was a Dutch school teacher who was involved in the early days of the project as a volunteer. Voorwerp means thingy in Dutch. The galaxy that was supposed to be classified was this main galaxy, and this is a HST image that was taken of this galaxy because it's so interesting, not the actual image that was used for classification, which I should add to this slide, but I don't have. What Hanny did was say, what's that weird fuzzy thing to one side? And it turns out what this is is evidence that this galaxy had a black hole that was an active galactic nuclei 30,000 years ago, but doesn't have one now. And that's very cool for understanding the timescales that black holes turn on and turn off in the centers of galaxies, in terms of the black hole's always there, right? But is it actively accreting and doing exciting things, or is it just in a sort of quiescent state? So yeah, a pretty exciting finding from Galaxy Zoo, and one of our best examples of a rare thing or a question that wasn't being asked that the crowd can answer. There are other examples, of course, but this is our poster child. Another reason to keep doing Galaxy Zoo is, of course, that we believe it's pretty effective public engagement. We see people enjoying using this just as a hobby, using it in the classroom. It's not a requirement to be into public engagement to be on the Galaxy Zoo team, except that we do have a requirement to kind of feedback our results to the crowd. And we do have a crowd who are really interested in our results. So we tend to attract people who are into public engagement. So here's some images of the team over the years doing various kinds of public engagement. Brooke Simmons, I think this is Adler Planetarium being interviewed. This is Tom Melvin, who was a PhD student who worked with me a few years back, working with a child on Galaxy Zoo. Obviously, Chris Lintar is famous example of this. He, as a BBC Sky at Night presenter, here he's pictured with Patrick Moore, and he's written a book about crowdsourcing and adventures in the Zooniverse. And then Becky Smethurst, who some of you know as Dr. Becky on YouTube, is a team member, a longtime team member, even before she was Dr. Becky on YouTube. And so, these are just some examples of the public engagement that gets inspired by Galaxy Zoo and that just sort of happens alongside Galaxy Zoo. Galaxy Zoo is popular. It was popular when it launched. This was the BBC article from 2007 when it launched. That was, for a while, the second most emailed story on the BBC, July 2007. Feels like forever ago. Here, the chart of classifications per hour in the initial launch, so we're up to 40,000 classifications per hour. This really just hit something in the public where people got really excited about helping us classify galaxies. In this article, we hoped 30,000 people might participate in the project. In each paper, we thank those volunteers who we can associate with having classified in that data set. So there's 160,000 here, 200,000, 85,000. And even today, Galaxy Zoo remains the most popular, so the most clicked on project in the Zooniverse. I don't know when that will change. Sometimes presumably it changes, but so far, pretty much every time I go here to Zooniverse and look at most popular projects, Galaxy Zoo is up at the top. We're not getting 40,000 classifications per hour anymore, but we still get pretty substantial classification rates. So I picked this out. This is classifications per week, I think. Yeah, per week. And I picked it out to get the spike that happened when we put new James Webb images on the site. So that happens in Galaxy Zoo, all these universe projects. When you do something interesting, you can send out a newsletter and bring people back. But even at our sort of baseline, we're getting 25,000 classifications a week, which lets us really make some progress in classifying galaxies. People always ask, why do people do this? The most kind of objective answer I have to that is from this 2009 paper by Jordan Raddick, where he did a survey of user motivations. And we all kind of lean into this idea that the most popular motivation was the wish to contribute to original scientific research. So at the Zooniverse and Galaxy Zoo, we firmly believe that doing crowdsourcing with the goal of actually doing scientific research with the output is the way to make it be successful. If you just do it with a goal of wanting to do some outreach, that's not going to work. But if you genuinely have a question that you can genuinely best answer with crowdsourcing, this works great. It also means, of course, that we're quite serious about publishing with our results. I initially joined the team about a year after the launch and sort of became the first project scientist, in the sense that I was really helping to get the scientific team together, starting telecons, we communicate. And I'm really proud of that work. And as I said, proud to have taken over as PI a few years ago. Over the years, we have 86 now team publications, many, many more where other people are using our classifications because we put them all out publicly. We have a substantial number of papers with a substantial number of citations at this point. So, we're really an established method to contribute to galaxy evolution. And here's a little bit of a summary of some of the results we have over the years. I obviously don't have time to go into all of those in detail at all, but I thought I'd just highlight a couple of the most recent results. So this is some work from Tobias Haran, who's currently a postdoc in Toronto, using our Galaxies Sears dataset. So this is the first JWST dataset that we had up to look at the bar fraction and how that changes with redshift. Tobias was able to show that a significant number of galaxies have bars, even at really high redshifts, and also did some pretty careful work looking at biases introduced by looking at very distant galaxies. So you can see how the bar fraction here declines with redshift, but it has not yet gone to zero within the JWST redshift range. So that's very interesting. Becky Smethurst also has a recent paper that used the Galaxies Sears dataset, where she looked at this really interesting population of galaxies that are clearly disk galaxies, and you can kind of identify that without Galaxies from the shape of the galaxy, things that can be measured in an automated fashion, but they don't have features, they don't have spiral arms, they don't have bars, so they're not kind of condensing in the way that we expect. So that's very interesting. And we're sort of still working on some of the interpretation here, but it's something you really can't do unless you have Galaxies because you can't independently pick out the featured aspect. Oh, and if you're curious what a not featured disk looks like, well, it looks like a disk without features. So in the center of these things are these little elongated galaxies that I argue are all obviously disks to me, but don't have spiral structure and don't have other features. So that's what you see. In Galaxies when you get the answers that you ask for. So we have to be really careful about the questions we ask. But if you ask the right question, you get an answer to that question. So if we ask if you see features and you don't see features, the answer is you don't see features. Okay, so here's my takeaway messages from this part of the talk. Galaxies and Zoobot is this flexible tool to help classify large extragalactic data sets. We invite people to contact us if they have data sets of galaxies they want to classify. We're a pretty open team. Yeah, and we have a lot of people to help classify galaxies. I hope I was able to argue that machine learning alone won't solve all our galaxy morphology problems, although it does help a lot. I kind of didn't lean into this too much, but the motivation for Galaxies is that galaxy morphology is an important clue, which will help us uncover the history of galaxy evolution, and we use it in all these papers, and it's really complementary to other measures that we have of galaxies. Galaxies project is continuing to provide reliable and useful morphologies for statistically interesting samples, so we can keep doing science with it. And it is also effective public engagement. People want to help us do science, and so it's a good thing to keep doing Galaxies to give them an outlet for that. Not just Galaxies, of course, all of the Universe projects. And in preparing this talk, I was sort of, what is Galaxies and what is Galaxies not? So I would argue the answer to what Galaxies is that it's an ongoing and successful method for classifying galaxies. It's a way to leverage human skills on identifying shapes and features in images. And it's also award-winning public engagement. I haven't talked about the awards, but we have won some awards for the work we've done, which has been a pleasure. Galaxies is not just public engagement, however. It is public engagement, but it's not just public engagement. It's a useful research tool. We are not finished. We are not done. We did not only work with the SDSS images. We are really a technique where this can be applied to any set of data images, of galaxy images. Galaxies is not pointless now that machine learning is getting much better. It is complementary to machine learning, works best in collaboration with our robot friends. And of course, also just want to emphasize, Galaxy Zoo is not the whole of the Zooniverse. Many people get confused between Zooniverse and Galaxy Zoo. Galaxy Zoo came first. The Zooniverse was inspired because it was successful, but Galaxy Zoo is now just one of many, many projects in the Zooniverse, and we're delighted to be part of that family. Yes, so thanks to the volunteers. And please reach out if you want to ask me any questions about this part of the talk. I was asked to also talk a little bit about using Galaxy Zoo in the classroom. And so My first statement on this is it's fine if you just want to classify. We're really happy for people just to classify. So if you can use Galaxy Zoo as just complementary to let's learn about galaxies, now let's have a look at some galaxies, that's great. We invite anyone to classify, and we really mean that. And our data analysis technique can deal with the fact that you might have a kid in the classroom who's not going to take this seriously. That's fine. We know how to deal with that. So we really just invite you to classify. There's something kind of magical about really getting your hands on real data and really contributing to science. And as I was preparing this talk, I happened to get an email from a student here at Haverford who sent me this, that in a high school astrophysics class, he classified galaxies in Galaxy Zoo. That was cool. And he's been really, really curious about galaxies ever since, and now wants to do research in my group, which is fun. He's not the only student who's reached out to me like this over the years. I've been doing this for a long time now. So some of the students at Haverford weren't born when Galaxy Zoo started, which is a bit scary, but true. But there's just something kind of powerful about really contributing to science. And so I invite you just to classify. However, if you want to do more, we do have some resources. The Zooniverse over the years has at times had education staff. Right now, that's a bit limited, but there are resources available on the website. If you go to any Zooniverse website and scroll right down to the bottom, you see this kind of base thing, which has an education link. Hopefully you can see my mouse there. This is the direct link to the education page, and this is what you'll see when you go to the education page. Basically a bunch of links that I'm going to kind of walk through, and then I'll talk to you a bit more in depth about some of my experiences using Galaxy Zoo in the Astro 101 classroom here at Haverford. So this is our first kind of set. We have some online resources, Zooniverse in schools, Zooniverse for undergrads. Scroll down a bit more. It talks about exploring the Zooniverse classroom, that you can set up group statistics. So if you want to monitor how many classifications your students do, there's a way to do that in the Zooniverse. And that there's going to be some project-specific resources as well. So going to the Galaxy Zoo page now, in the About section in Galaxy Zoo, we do have an education tab. It's a bit limited, actually. And I think after preparing this talk, I'm going to add a little bit more to this. But basically talking about Astronomy 101 with Galaxy Zoo, and that we're also recommending some Sloan Digital Sky Survey education resources as potentially another way to get hands-on data. But let's take a look back at, let's see, what was this? This is, I think, now if we go to the resources for education page, it's kind of separated into different categories. So we see now Astro 101 for Galaxy Zoo, some resources from different projects. Again, Zooniverse in schools and Zooniverse for undergraduates. So I think I'm going to start with the Zooniverse in schools, which is not something I have any personal experience with, but I just wanted to walk you through what's there. So if you go to Zooniverse in schools, you find a bunch of resources. There's an introductory video about what Zooniverse is. And then under resources, there's two different activities that are actually Galaxy Zoo based. So one of them says it's the Galaxy Zoo activity, and the other one is the Zooniverse classroom activity. But if you go to it, it's mostly Galaxy Zoo. Starting with the Galaxy Zoo activity, this has an educator guide, which estimates that this is about 30 minutes in the classroom. Just invites you to go to the Galaxy Zoo website and classify some galaxies, and also provides a worksheet so students can kind of note down their own classifications. So then you can have an in-class discussion about what they learned doing this. And then there's some actual skills about making tally charts along the way. I noticed while doing this, there's also some additional hands-on activities that might be recommended or might be nice complementary to these online things. And I'm recommending my student public outreach group here that we might want to try the Galaxies Jars activity, which is like build a galaxy in a jar, which is kind of fun. But anyway, just pointing out there's some hands-on activities that the Zooniverse education team like. The second activity was Zooniverse in schools. It's a slightly longer activity that requires logging into the Zooniverse classroom, which I'll cover in a minute. And just the other thing to say about this is that both of these come with a class video, which is my colleague Chris Lintott talking about why we want to do this and why this is interesting. So some nice resources here for classroom use. What I have personal experience with is Universe activities for undergraduates, particularly Astro 101 with Galaxy Zoo, but just pointing out that there's also some Planet Hunters resources and Planet 4 resources. These are two other Zooniverse projects that are astronomy related. So if you prefer exoplanets or Mars as your base for the data you explore, that might be of interest. So back to Astro 101 with Galaxy Zoo. If you go there, you'll see that there's an instructor guide with a whole bunch of suggestions for how you can use this. And then it will also encourage you to log in and create a classroom. So when I logged in, while I was preparing for this talk, I was able to see that my Haverford Astro 101 classroom is still there. I did this 5 years ago at this point, so it's a little bit out of date. But I did make a classroom for the workshop. So it's called the 7th Shaw-IAU Workshop classroom. Here is the join link. It's not particularly easy to pass. Hopefully there's a way that I can communicate this link with you so you can click it and see if you can play along. There are different projects that you can participate in that will be in your classroom once you create it. So Galaxy Zoo 101, Hubble's Law 1, and Zooniverse in Schools. They have custom projects associated with them that are just for education. That's not because, I just want to emphasize, that's not because we don't want your classifications in Galaxy Zoo, but these custom projects just let us kind of illustrate what's going on a little bit easier in some ways. So I'm going to invite you all to join the Galaxy Zoo 101 project. So this is the project link for that. And if you join that, you should see a Galaxy Zoo-like interface. This is a separate, not the main project, and it has 22 curated galaxies in it that maybe are a little easier to classify than some of the actual ones where we're asking for help with research classifications. But other than that, it's pretty much identical to Galaxy Zoo. So again, hopefully we can share this link more directly. The instructor resources will have guides for like how you communicate with your students to interact with this. And so if I move the Zoom controls, so you have to use this project link and you have to see this banner you're classifying as a student in your classroom. And you can kind of work on this activity together, and then as an instructor, you can download the collected classifications of your class. Typically, and in this Astro 101 activity, the recommendation is the students also record their own classifications separately, because one of the sort of educational tools or educational goals here is how when you have a crowd, your own personal classification might differ from the crowd, and why that's interesting and where that tells you something about Galaxy Zoo, galaxy classification and galaxies in general. And this activity also has some guided discussion about how this applies to other places where we crowdsource data, like reviews online or all kinds of different things like that. I haven't done this, I don't think, in the classroom yet. As I mentioned, it's been a few years since I taught Astro 101. What I do remember doing is the research project, which again is in the instructor guides. And so this is a slightly longer activity for Astro 101, where the class will use, in small groups, will work with a simplified version of a data set from a paper actually I published about 15 years ago now. This was the paper in Galaxy Zoo where we pointed out that some fairly substantial fraction of spiral galaxies are quite red, almost as red as ellipticals, and that the whole spirals are all blue, ellipticals are all red by modality is not quite as simple as that, typically, in galaxy evolution. So I provided, or I made a curated version of that data set that's a bit simplified. So, but it has still, it's real data though. It has morphology, it has magnitude or brightness measurements, so you can construct color, and you have to teach about astronomical color. It has information on galaxy environment, galaxy mass, axial ratio, and physical size. And you can use that data to identify a bunch of different scaling relations in the galaxy population. And it's all on a Google spreadsheet. So for Astro 101, I thought that was quite beneficial. We're learning spreadsheet data analysis. You can do some fairly sophisticated things, and it's maybe skills that that population of students might be more likely to use in the future than other data analysis skills. The instructor resources sort of goes to a Google Drive with a bunch of various things. There's a long instructor's guide, which would sort of explain what all the different things are. Students are kind of guided through doing this research project, coming up with a question, learning a bit about galaxies, and then doing like a video report at the end. So there's an example question here. Are all ellipticals red and all spirals blue? Calvin and Hobbes worked on this together with the data set and discovered that the mean color of the spirals was 0.5, whereas the mean color was 0.7. And they had to know that that mean ellipticals are typically redder than spirals, which is absolutely true. And they also kind of have some pictures of different kinds of galaxies. So yeah, so I did this in class. Yeah, it has some example timelines as well that are suggested for how you kind of weave this in with all the like learning about galaxy evolution, how you would then fold in this using Galaxies data to learn or to do a sort of guided research project. Here was my implementation of this. I did this in spring of 2020, so that was really interesting. I had intended to do it before we knew that we'd be teaching entirely virtually after spring break. And then I obviously did it entirely virtually. So you can see my syllabus here kind of interweaves. We met 3 times a week by Zoom, but it was mostly like discussion by Zoom. I had them watch a lot of videos, some videos that I made and some that I got. This is the CC stuff is Phil Plate's really nice YouTube series on intro astrophysics that I used because, this was all pivoting really quickly to online teaching, right? So you can see some of the Galaxy Zoo and learning about galaxies interweaved with other stuff, and also the list of assignments they did. So when they were handing in their key plots and their videos, we did peer review. This had some challenges. I mean, it was during the pandemic, so that was one thing. But I did also find that a lot of my Astro 101 students were quite scared of the idea that they were doing research. On the other hand, they all pretty much did an awesome job. That's what I remember, that the videos were charming. They actually revealed real things about galaxy evolution. And I hope they learn a lot more from this than just me telling them about galaxy evolution. Also, I mean, honestly, it was spring 2020, so anything good seems like a win. So I was proud of how this went. I am currently about to teach Astro 101 again, so I'll be teaching it this spring, and I'm considering how to fit this in the schedule for that. I have some other plans as well, so we'll see how that goes. But if you're interested in using this or want to talk more about it, please reach out. And if I'm able to be there live, I'll be there for questions. But otherwise, in addition, you can reach out to me at my email or on Blue Sky. Yeah, thanks for listening.